Okay, so we just do a little short, quick recap for what we have learned before your holidays. Okay, so if you still remember the short ID that Madam gave you, ABC square ID. What does it stand for? Hold on. Okay, can anyone tell me what is Avogadro's law? Avogadro's? Anyone want to tell me about that one? Just a quick recap on this. Nak dengar tak apa yang Madam tanya dekat sini? Anybody's home?
Yes, madam.
Avogadro's law? What is it about?
Volume of gas is directly proportional to number of moles.
Okay, very easy one. Just to start on your memories. Yeah, volume of the gas is directly proportional to number of mole or the amount of the gas. How about Boyle's law? Volume
Inversely proportional to pressure.
inversely proportional to pressure. The experiment for those who have already did it, something to do with the Boyle's law. Okay, and how about Charles? How about Charles' law? I have 85 of you.
Volume of gas directly proportional to absolute temperature.
Okay, what it means by absolute temperature? It must be in which unit? What is the unit? Kelvin. Okay. And then your combined gas law, we're combining between your Boyle's and Charles, and ideal gas law, you have a formula. What is it? Ideal gas law? What is the formula for ideal gas law?
PV sama dengan nRT.
Okay, very good. PV equals to nRT. A quick review, unit for pressure, it must be an ATM. Volume must be in liter. And then this one, definitely mole. And then we have the temperature, it should be in Kelvin. And most importantly, your gas constant R, you have a value of 0.08206 with the unit of ATM, liter per mole per Kelvin. Unit mesti kena ingat Kalau liter, we can also use for DMQ. Either you use liter or you use DMQ. Okay. And then for our the last lesson before our holiday, not the last lesson, the second last lesson, we have talked about the Dalton's law. Okay, so Dalton's law, it referred to the unreacting gases. The total pressure is the sum of the individual partial pressure. Okay, so if let's say in a container you're containing gas A, gas B, gas C, then we need to total up all the partial pressure to get your total pressure. Okay, so that one's referred to your Dalton's law. And then let's see, where did we stop last time? Okay, so this is where we stopped lah. And then also the questions example, we have question number 1. Okay, and also question number 2 over here. Okay, so in your semester break arrangement exercise, also you have a questions related to Dalton's law. Okay, so for what Madam have already checked so far, the answer is alright lah. Okay, but I will give you the answer for your own checking for the sem break enrichment questions. Okay. So to continue with your Dalton's law, So now we want to look at the application, applications of Dalton's law. Okay, please remember over here. Okay, we have the applications of Dalton's law when you see water displacement method. Or sometimes the question will say, what kind of gas is collected over water? For example, oxygen is collected over water, chlorine gas is collected over water, or hydrogen gas is collected over water. So both of this means that we need to apply your Dalton's law. Okay, so when a gas sample is collected over water, a mixture of gas and water vapor is collected. Okay, so when you have two type of gas, two different gas, that is a mixture. Okay, but both of them is not reacted. So we will apply this Dalton's law. So if looking at the diagrams over here, if let's say we are reacting, we have some reactions going on inside your conical flask over here. So you're producing some of the gas. Doesn't matter what type of gas lah. Maybe oxygen, maybe hydrogen, or whatever. Okay. So when this gas is produced, okay, it will go into the test tube to come over the area over here. So can you see my the place that Madam drawing over here? Boleh nampak apa yang Madam
Okay.
tulis?
Yes.
Okay.
Yes, madam.
So the gas collected over there, it will pass through your water. So when it pass by the water, when the bubble bursts into the air, so this column, this space, we will capture both the gas that we want, okay, and also the vapor, because it passed through the water over here. So this is what we call as the water displacement method. So you always remember lah, water vapor is a compulsory partial pressure inside the Dalton's law using water displacement method. Okay, so we try to use this concept to answer one of the example questions. So let's look at this one. Okay, by using water displacement method, so very clear lah, we want to apply our Dalton's law. Okay, 128 milliliter oxygen gas was collected. So 128 refer to the volume of our oxygen gas. So you may need to write down what is the informations we have. Okay, from the decompositions of potassium chlorate at 24 degrees Celsius. So this is the temperature. Okay, and the atmospheric pressure of 762 millimeter mercury. Okay, so imagine here we have a process. When we burn our potassium chlorate, yang ini kalau tak nampak boleh tulis besar sikit lah. Ini contoh yang Meda bagi. Tak ada dalam nota ya. Okay, you can simply draw your own diagram. But just to let you know, when we burn the potassium chlorate, okay, burning of potassium chlorate will release oxygen gas. So this oxygen gas will pass through this delivering tube and then go through the water, and we are collecting inside this area, okay, this space. So when it passes by the water, we are capturing or collecting your oxygen gas as well as the water vapor. So over here, you apply your Dalton's law. If it say that the water displacement method occur at atmospheric pressure 762, that means inside this area, we have the total pressure of 762 millimeter mercury. Maksudnya dekat sini dia bagi teruslah total pressure dia. Okay, 762. Maksudnya dia adalah total pressure yang ada dalam container ini. Okay, so we can do our own formula of Dalton's law. So let's see. So by applying your Dalton's law.
Madam,
Yes.
Madam, O2 plus H2OG, why gas?
Why gas?
Yes.
Partial pressure. We are looking at the gas. So imagine now we are collecting your oxygen inside bubble. So when this bubble bursts, dia pecah kan. So sekali dia minyak air akan ada water vapor. So maksudnya dalam area ni memang ada oksigen, ada vapor. Gas yang dalam bracket ini adalah gas lah. Gas dengan vapor adalah benda sama lah. Is that okay?
Yes, madam.
Okay, so kita lukiskan kita punya formula So Dalton's law. Total pressure equals to, how am I going to continue? So since I already know I'm collecting both the O2 and H2O inside the area there. So what should I write for the formula of my Dalton's law? PT equals to?
PO2 plus PH2O.
Okay, plus pressure, partial pressure of the vapor, of the gas H2O, yeah? Okay, so just now over here we have already mentioned 762 millimeter mercury refer to the total pressure. So now what we want to find? What is it missing inside this equation? Value untuk oxygen ada tak? Partial pressure oxygen ada tak?
Ada.
Ada. Partial pressure oxygen we don't have. But if we continue the questions over here, we see calculate the mass of oxygen gas obtained, the vapor pressure of water at 24 degrees Celsius, temperature dia sama ya. Okay, was 24 millimeter mercury. What does this sentence means? Apa maksud soal ayat ini?
Pressure water.
Pressure of water, right? Vapor pressure of water. So that means your partial pressure of the pH2O over here, we have a value of 24 millimeter mercury. So apa yang kita nak cari dekat sini? What do we need to find? Pressure of
Oxygen.
oxygen. Okay, so try to find your pressure, partial pressure of oxygen in millimeter mercury first. Okay, so what will be your values? Okay, 738 millimeter mercury is the unit of the pressure that I need. Is millimeter mercury the pressure that I need?
No.
Kita tak tahu kan, so tak apa, kita tulis dulu. Millimeter mercury. Okay, so let's just go back to the questions again. In the questions, we have the volume of oxygen. Volume sudah ada. Temperature ada tak? Temperature of the system we have or not? Dah ada kan? 24 degrees Celsius. Okay, so now you have already find your partial pressure oxygen. What is actually the questions asking? Soalan nak tanya apa?
Mass of oxygen.
Okay, before you find the mass of oxygen, what is missing, or what is the thing that we need to find first? Kita perlu carikan. Kita perlu carikan apa? Kalau nak carikan mass oxygen. Number of mole. Okay, so we have volume, we have temperature, we have partial pressure, and we need to find the number of mole. So we need to apply our PV and RT. Okay, so tell me about your PV and RT pressure in PV and RT. What is the unit that we need to use? What is the unit you need to use?
ATM.
ATM. So you need to do a conversions of unit. So 738 millimeter mercury convert into ATM before you do the substitution using the ideal gas equation. Okay, so try to convert partial pressure of oxygen 738 millimeter mercury into ATM. I hope you still remember lah. 1 ATM equals to 760 millimeter mercury. So 738 divide by 760 to get how many?
0.971.
Okay, very good. 0.971. Okay, 9711 also accepted because you will get a value of 0.97105 something. Boleh accept lah kalau 0.9711.
So we can also take only 3 decimals
because
for
behind
the
it is
answer.
0. Yes.
Oh, so if it's not 0, so we have to take 4.
Yes.
Alright.
Okay. So PVNRT over here, we have already the partial pressure of PO2. Kenapa kita nak tuliskan abbreviation PO2? Is because in this question we have total pressure. Okay, we have the vapor pressure of water. Okay, so you need to indicate what pressure are you using. So since we want to find the number of mole of oxygen, then we put the partial pressure of the oxygen. Volume, also volume of the oxygen gas. So if you go back to the questions, 128 milliliter of oxygen gas was collected. Okay, so over here, you just need to substitute the values inside it. So in order to find your number of mole of oxygen gas, you try to rearrange a little bit for your formula PV and RT, and then you do the substitution. Pressure, we have 0.971, the one that you have converted just now. The volume should be in the unit of liter. So 128 milliliter convert into liter. It will be 0.128. Nah, boleh terus to convert, tak ada masalah tapi awak kena clear apa yang awak tengah buat. Okay. Value of the gas constant 0.08206. And how about the temperature? How about the temperature? Do I need to do anything with the temperature?
Convert into Kelvin.
Okay, so and the values will be 29 24 plus 273.15, yeah, and then you will get 29
715.
7.15. Okay, very good. Try to find the number of mole of your oxygen. And then finally, to find the mass of your oxygen gas. So mungkin ada orang yang akan tanya, Madam, kenapa bukan O? Kenapa O2? Remember what Madam tell you before? If the question say oxygen gas, it refer to O2. If the question say hydrogen gas, it refer to H2. Nitrogen gas, we have N2. Then we have F2, Cl2, Br2, I2. So if it refer to oxygen gas, then you straight away O2. Okay. So after you finding the number of mole of our oxygen gas, you need to times with the molar mass of oxygen. So molar mass of oxygen over here is 32. So try to find the mass of your oxygen gas in this case. Okay. Let me know if you have found your answer, yeah?
0.1631.
Okay, 0.1631. So everyone's agree?
Agree.
Agree.
Yes, madam, agree.
Okay, 0.1631. Very good. So this is the example questions that we apply the Dalton's law. Remember, when we're using the water displacement method, okay, we will have two different gas inside the column that we collected here. One of it will be water vapor, another will be the gas that you want to collect. Okay, so let's look at another questions over here. Maybe I have give you a list of exercises. Yeah, over here, question number 1 until question number 6. Okay, this one is for your own practice for your Dalton's law. Okay, then Madam will show you one more example for question 5. Cari dulu soalan dekat nota awak. Question number 5, yeah. Okay, so are you ready for these questions? Dapat
Yes,
cari tak
whether
dekat nota, dapat cari kat mana? Jumpa tak soalan dia?
Jumpa.
jumpa.
Jumpa ya. So buat ya. Okay, so acetylene is produced in laboratory when calcium carbide reacts with water. Okay, so for a sample of acetylene collected over water. So this is the keyword. Okay, the questions have already give you clue that we need to apply Dalton's law when you see collected over water. So now it gives you the total pressure, 738 torr. Okay, and the volume is 523 milliliter. So at the temperature of the gas, 23 degrees Celsius, vapor pressure of water is 21 torr. Determine the mass of acetylene collected. So target sekarang dekat sini nak kutipkan mass untuk acetylene. Formula is already given lah, C2H2. Okay. So for those who, if you want to make it clearer, or if you can't understand how to apply Dalton's law, maybe you want to draw a simple diagram. So let's say this is a reactions that happen between your calcium carbide, okay, together with water. So when you collecting the gases, tak berapa cantik, tak apa, tapi awak kena fahamkan awak punya konsep. Yeah, so this is the water. Okay, so over the area here, we have collected, of course, first one is your water vapor. Okay, and another guess what is collected inside this area? What other gas is collected inside this area? Beside H2O. Gas apa yang kita nak collect selain daripada vapor pressure?
Acetylene.
You only get one gas over here. The sample is already set for a sample of acetylene. So beside your vapor pressure of water, your H2O gas, we have also the acetylene, C2H2, which is our target. Okay, so applying your Dalton's law, the total pressure equals to the partial pressure of the vapor plus the partial pressure of the acetylene. Okay, so try to find the partial pressure of the acetylene over here. 738 is for the total. For water, we have 21. So in this case, what is the partial pressure of our acetylene? Okay, try to figure out in ATM. All right, what is the value in ATM for this partial pressure of acetylene?
0.9434.
Okay, 0.9434. Do you agree?
Yes.
Yes.
Dapat ya? Okay, so 0.9434. Because after you subtracting the 21 for 738, you got 717 divided by 760, you will get about this value. Okay. But first of all, you need to show your calculation in TOR first before you convert into ATM. Okay, so in order to get the mass, so similar like our question just now, we need to find the number of mole of acetylene. Okay, so applying same thing, your ideal gas equation, our PV and RT. But in this case, pressure for acetylene, volume, acetylene as well, number of mole acetylene, then gas constant and temperature. Okay, so apply your values and then we see what is your value for number of mole first, yeah? The formula you need to write down lah, especially for this one. Yang ini nak susun balik awal nak terus isi value tak ada masalah. So let me know what is your value that you got. Don't forget to change the unit for the volume of the gas. 0.523. Okay, what's the mole that you got over here? Dapatlah jawapan. Nama dia bila orang jawab ke?
0.0203.
203. Ada answer other than this one? 0.0203. Ada lagi yang lain? Semua sama?
Sama, madam.
Sama, madam.
Sama, madam.
Sama ya. Okay. How about the mass? Anybody got the mass? 0.5? 2?
5, 7, 528.
Okay. 528. 5278. Okay, accepted. 0.528, 0.5278, even 0.53 also, madam, will accept lah. So make sure you understand the concept of the Dalton's law is to apply your over here this concept, and then other than that, it's just applying your ideal gas law. Okay, if you want to use the
What's the weight?
formula,
What's the mass, madam? Just now.
the mass 0.5278 or 0.5.
Oh, I
53.
miscalculated. No wonder the answer is different. All right.
Okay, so can try to apply this concept for other exercises as well. Yeah, we can see over here you have question number 6, also applying the concept of the water displacement method. So you can try to use the concept and then apply your calculation. Okay, so homework, the homework to be submitted in GC later, yeah? In the exercise number 3 over here. Or you want to jot down, can also. Madam, select a few questions for you to practice. Okay, and then to be submitted into Google Classroom. So you go to the exercise number 3 over here. And I want you to do question number 2, number 3, and question number 4. Okay, so applying over here, you can see Dalton's Law, Boyle's Law, Ideal Gas Law, then kita apply and practice lah. Okay, so question 2, question 3, question 4 into GC. Is there any questions?
No, madam.
No, madam.
Okay, sebab lepas ni madam nak masuk subtopik yang last kali untuk topik 5.1. Okay, so until this point for Dalton's Law, Ideal Gas Law, any questions you would like to ask before we proceed? Ada soalan nak tanya? Today you are a little bit quiet, ya?
Tak ada.
Ke sebab madam pakai mask, you tak nampak? Tak jelas ke suara madam?
Jelas,
The
madam.
last, madam.
Madam, jelas.
Jelas ya? Okay. Right, so let's just proceed to the next one. Is hold on a second now. Okay, our next part is the ideal gas law and real gas. Okay, so let's just look at the ideal gas first. Okay, we can see over here, we will go through the notes together. Ideal gas law, it refers to the gas having your ideal behavior. Okay, the gas that obeys the ideal gas law, we got our PV and RT. Okay, and then ideal gas law also follow kinetic molecular theory. If you want to refer back, in the very first page of your 5.1, we have the kinetic molecular theory, the five postulate. The gas particle constant and random motion, collision between gas particle are elastic, volume of the gas particle is negligible. Highlightkan point yang ketiga kalau ada nota ya. Okay, and then point number 4, intermolecular forces or attraction repulsion forces are negligible. Okay, point 3 and point 4 are very important. And then point number 5, average kinetic energy of gas particle are directly proportional to the absolute temperature. So this is the 5 postulate for kinetic molecular theory. So for any of the gas that behave ideally, they follow kinetic molecular theory. That means the intermolecular forces between the gas particle is negligible. Masih ingat lagi tak negligible maksudnya apa?
Can be ignored.
Ignore.
Can be ignored, boleh diabaikan ya. So because it is very small, and we can straight away ignore it. But that one is only for ideal gas. Okay, one more thing, the last one, yeah. Volume of the gas particle is negligible if compared to the volume of container. Okay, because the volume container is huge, volume of the gas particle become very small, very tiny until it can be ignored. Okay, so if you look at the bottom 2 points over here, these two bottom point is very important for you to recognize the differences between ideal gas and the real gas. So we look at here, ideal gas, we apply the ideal gas equation PV equals to nRT. So how about real gas? Real gas. Another words for real gas, it is non-ideal. The real gas behave, or we can say the real gas is less ideal. Tak perfect sangat lah kalau untuk real gas. Okay, so in this case, the real gas, it do not obey ideal gas law. So that means for this real gas, they have their own equation. So I'll introduce this one to you in a while. Okay, real gas also do not follow the kinetic molecular theory. And the very important one, the intermolecular forces between the gas particle for real gas is significant. So over here, you can see a very strong differences. Ideal gas can be ignored, but real gas, it becomes significant. It cannot be ignored. Dia ada dia punya value, dia ada dia punya effect. Okay, and then the last one over here, talking about the volume of gas particle, also significant comparing to the volume of the container. So please take note. Ideal gas, we ignore. We ignore both the intermolecular forces and also volume of the gas particle. But for real gas, we take it into consideration. Okay, because intermolecular forces is significant, volume of the gas particle also becoming significant. Okay, so highlight 2 of this point, important. So we want to look at this one, condition. So bawah awak punya nota selepas table ke atas tu, kat bawah kita ada tempat kosong yang madam nak awak isi kan. Okay, so we look at the column for ideal gas first. You look at this one, condition for ideal gas. Okay, so this condition is at which the real gas approaches ideal behavior. Ada main sikit dengan grammar and the English, how the sentence is constructed. Okay, a real gas approach the ideal behavior, meaning that a real gas become more ideal. Dia lebih kepada ideal gas. Punya pattern lah. In negligible intermolecular forces, negligible volume of the gas particle. Okay, so you can highlight over here, approach, idea. The keywords over here, more idea, idea. Okay, so where you can find an ideal gas. So usually it can find at low pressure and high temperature. Please remember two of this condition, low pressure, high temperature. So in detail, let's just look at this and then fill in together with me. Okay, low pressure. So at low pressure, what happens to the volume of the container? If we apply Boyle's law, what happened to the volume? If we know that Boyle's law, the volume is inversely proportional to pressure. So low pressure, what happened to the volume?
Increases.
Increases. Okay, so volume become bigger and bigger at low pressure, yeah? So what happens to the gas particle? Is it staying close together or being far apart?
Being far apart.
Far apart. So this one makes sense. When your container become bigger and bigger, your gas particle becomes further apart. Become further apart. Okay, so when they are located far from each other, intermolecular forces become, what is the keywords if you refer to ideal gas? Yang tadi madam bulat ni kan, apa keywords dia? Intermolecular forces become? So if madam try to draw a diagram, if let's say over here, you have a very big volume over here. So comparing to the volume of the particles, the one that madam dot over here, you can't even see it over, right? So what happens to the intermolecular forces between all these gases particle?
Negligible.
Become negligible because the volume of the container is so far away. Make it so far away. So the intermolecular forces become negligible. Negligible. Try to practice the spelling, yeah? Yeah. Okay. Volume of the gas is also negligible comparing to the increasing volume of container. Okay, so volume of the gas is also negligible. Therefore, we can say that this gas obey kinetic molecular theory and it behaves ideally at low pressure. So low pressure, you have to link it with the volume of the gas. You have to link it with the intermolecular forces. Okay. Any questions for the low pressure for ideal gas? Ya, ada kait dengan teori yang kita belajar sebelum ini, ya. But you just need to remember about the condition. The explanations can link. You can link it using the short point over here. Right. Any questions for low pressure?
No, madam.
Okay. So next conditions over here, we have high temperature. Remember that madam tell you that temperature, we have to link it with kinetic energy. Okay, so if let's say you have a high temperature, kinetic energy, what happened?
Increase.
Increase. Kinetic energy increases. So this gas particle will move at high speed, or they will move faster. Gas particle will move faster, gas particle will move at high speed. Okay, so gas particles are free from attractive force. And we can say that the intermolecular forces of these gas particles are negligible. Okay, why do we say so? If you refer back to this diagram, if let's say I increase the temperature increasing. So all this gas particle, if I change a little bit of colors, yeah. Okay, all this gas particle, they move at very high speed. Dia bergerak cepat. Madam tukarkan warna, Okay. So let's say they move very fast. Over here, over there. So that means the intermolecular forces to attract them become very, very small. Because they now move very fast. You want to capture them also very difficult. Susah. Dia susah nak ada forces antara satu sama lain. Okay. Therefore, we can say intermolecular forces become negligible. Okay. So remember, temperature, we link it to kinetic energy. Okay. So please fill in the blank. Low pressure, high temperature for ideal gas. So when a gas is approaching ideal behavior or a real gas becoming more ideal. Okay, condition for real gas is the opposite only. So the opposite. So let's look at this one. So condition for real gas, please pay attention to the sentence. Okay, how they mention the situation. Okay, so at which a gas deviate from ideal behavior. Perkataan deviate, maksudnya ialah apa? What is the words deviate means? Any suggestions?
Different.
Different? Okay, accepted. Lagi? Apa yang awak faham pasal deviate? Deviation? Deviate? Ada tak?
Menyimpang. Menyimpang.
Menyimpang. Mungkin your friends can understand. Okay, deviate that means kalau dalam Malay terlepas landasan. Okay, we say is away from this idea behavior. Away, lagi jauh daripada idea. Or in another words, we can say this gas becoming more real, more non-idea. So kena perhatikan awak punya ayat soalan tanya dia condition untuk apa. Okay, so at which gas deviate from ideal behavior or at which this ideal gas become more real. So keywords over here, becoming more real, more non-ideal. Okay, this deviation is due to the real gas particle occupies space and has volume. So if in compare, you see, just now we say ideal gas, dia punya volume sampai negligible, boleh ignore. Ini ideal gas. Satu dot saja tak nampak. But in fact, the real gas, okay, the particles, the gas particles does actually occupy space and is very big. Sampai kita tak boleh ignore. Okay, this is what happens to real gas. Real gas particle occupies space and has volume. Okay, so another thing over here, real gas also having intermolecular forces. Because they occupy space, it become closer together. Therefore, you have the intermolecular forces. Kita patah balik kepada jadual table ke atas. Real gas have a significant intermolecular forces. Real gas has significant volume of the gas particle. Okay, so deviation is more significant when it happens at high pressure, low temperature. Dia terbalik daripada condition untuk ideal gas. Okay, so let's look at the high pressure first. Okay, at high pressure, what happens to your volume of the container?
Decreases.
Decreasing. So when the container becomes smaller and smaller, your gas particle become how? Kita dah compress kan awak punya container kan, dah compress. So the gas particle become closer to each other. So when they're getting close to each other, there will be attraction forces between one another. Therefore, your intermolecular forces become more significant. Mesti kena ada keywords significant ataupun negligible. So volume of the gas also become significant. So this, both of this is the keywords for a real gas condition. In intermolecular forces, any matter short form lah, you have to understand that in IMF, for in this case, means the intermolecular forces. The IMF become more significant. Volume of the gas is significant compared to volume of container. Make sure tak boleh mention volume saja. Mesti bagi tahu volume apa. Awak nak mention volume of the gas ke volume of the container? Okay. So any questions for the condition of high pressure of the real gas?
No, madam.
Okay, kalau tak ada low temperature pula. Nah, kita kaitkan balik dengan kinetic energy. So low temperature, what happens to your kinetic energy? So it is directly proportional, yeah. If you have low temperature, kinetic energy automatic will
Slow.
decreases, becomes smaller, becomes lower. Okay, so the gas particle move at slow speed, or we can also say the gas particle move slower. Okay, so when it moves slower using the diagram over there just now, yang tadi dia cepat, yang sekarang ni lambat. Nak move over. Over here, tiba-tiba dia stop dekat sini. Ada attraction pula. So when it is slow, it means that there will be some attraction forces between the particles. Or in another words, our keywords over here, intermolecular forces become significant. Okay, so please bear in mind over here, we only have two conditions, each of them, pressure and also temperature. Okay, ideal gas, low pressure, high temperature. Real gas, we have high pressure, low temperature. Kalau susah nak ingat, awak ingatkan satu set. Hafal untuk ideal gas saja. Nanti untuk real gas, dia terbalik. Opposite only. Okay, so over here, is there any questions you would like to ask? Can I proceed to the next one?
Can, madam.
Okay. So the next one, we want to talk about the equation for our real gas, which is called over here. So to recall back, if you have an ideal gas, we have a formula of PV and RT. Okay, so if you want to look at the equation for a real gas, this is what we have got, the van der Waals equation. Okay, so let's look at in detail what is the functions of van der Waals equation or a real gas equation. So this equation is to describe the real gas behavior. Okay, to describe the real gas behavior. And in this van der Waals equation, also it takes into account your significant intermolecular forces and your volume of your gas particle. Because in real gas condition, we have this significant intermolecular forces, okay, and the volume of gas particle. Okay, so both the constant A and B are van der Waals constant. So if you look at over here, it's quite similar to our ideal gas law. Ideal gas law, we have PV equals to nRT. But since real gas, we have significant intermolecular forces. So dekat sini dia ada terms baru. Okay, AN squared over V squared. Some of the reference book or in your lectures not it write like this. Sebenarnya dia sama je ya. AN square and 2 square, N square A sama je. Okay, and then we have another correcting factors for the V term over here, volume. We have this one, MB. But don't worry, A and B, they have their own meaning. So I have written down over here for you. Okay, so value of A, collecting factor, A N square, A dekat sini. This A constant. Okay, value of A indicate the strength of intermolecular forces between the gas particle. Okay, and the higher value of A, we will say that the intermolecular forces is stronger. Okay, please fill in the blanks over here. Higher value of A, stronger the intermolecular forces, and the gas is said to be more real. Because real gas having significant intermolecular forces. So if you have a strong intermolecular forces, the gas is more real. Okay. So in terms of AN square over V square, sebenarnya dia punya unit sama dengan pressure. Sekali lagi, pressure punya unit dia lah apa? So let's say P plus the terms over here. So pressure, what is the unit?
ATM.
ATM. Okay, so pressure in the ideal gas law, we have ATM. So maksudnya term dekat sini semua ada ATM punya unit. Pressure as ATM, this one has ATM. The whole terms over here, we also have a unit of ATM. So let's just see what is the constant A's unit. Kalau kita nak buat derivation boleh juga awak boleh catat dekat tepi. Dan nak carikan unit untuk A. So let us see. So in order to find your units of A, we just make equalization. And nak ikut sini pun boleh, nak ikut N square A pun boleh ya. Okay. Over V square equals to ATM. N is the symbol for number of mole. So let's just put the unit for mole for your N over here. So mole to the power of 2. Volume unit dia ialah apa? In PVNRT, unit for volume is
Liter.
liter. So we have L square over here equals to ATM. Okay. Hold on a second. Ada nak adjust dulu hotspot. Okay, so let's just do the unit for A. What is the unit for A? Sorry madam, punya hotspot macam tak berapa stable. Can you still hear me?
Yes.
Yes, we can still hear you.
Yes, madam, we can stay.
Okay. So what will be the unit for your A constant?
ATM L square mole per mole square. Is it?
Okay, L square over kita tulis balik ATM dulu. Lepas tu kita arrange balik A punya unit. So ATM L square over mole to the power of 2. Do you get this?
Yes, madam.
Okay. So same thing for MB. Later we will check for the unit for the constant B. So let's just look at what is the functions of our constant for B, constant B in van der Waals equation. So value of B indicate the size or the volume of our gas particle. So remember that in our real gas, we have a significant volume of the gas particle. So value of the B indicate the volume of the gas particle. And if you have a bigger value for B, we have a bigger volume of the gas particle. Okay, or bigger size of the gas particle, and then therefore we can say this gas is more real. Okay, so a summary over here, lower value of A and B indicate that the gas behave more ideally. Lower the better lah, lower the more ideal. And then the higher the value of A and B, It means that the gas is behaving more real or more non-ideal. Less ideal. Boleh tulis kat sini. Dia ada banyak words boleh tulis less ideal. Or deviates more from deviates more from ideal behavior. It has different patterns of how you explaining. Becoming more ideal, more real, more non-ideal, less ideal, deviates more from ideal behavior. Okay, so if you look at the terms over here, we have V minus MB. So it's the same thing. The whole terms over here, same with the PV nRT in our ideal gas. So if you can see over here, if the liter or the volume over here, we have the unit of liter. Therefore, in the term MB over here, we also have the unit of liter. Then only you can do the subtraction. Okay, so MB equals to liter. We want to figure out what is the unit of our unit for our B constant. So, madam tulis balik kejap. Unit B. Okay, so MB equals to liter. So N stands for our number of mole. Therefore, for B, we have the unit of N maksudnya dia adalah mole. So what is the unit for your constant B?
L per mole.
Very good. Okay, this one is just an extra information for you, as you can jot down over here. So PV nRT, and then you have the van der Waals equation. The terms is still similar, but we have take into account your intermolecular forces and the volume of gas particle. So dia cuma adjust sikit untuk equation PV nRT. Equation dia adalah fixed dekat sini. But you just have to remember about what it means by the value of A, what it means by value of B. Sorry, madam tak dapat nak enlarge. Nak enlarge sikit tak dapat. Okay. Alright, so dekat sini ada soalan tak? Unit je, value A, B ke? Yang mana satu kurang faham? Nak madam explain sekali lagi. Can you follow?
Yes.
Yes.
Madam,
Yes?
so we only going to use this formula when it is stated that it is real gas?
Yes. No calculation lah. But you have to know what is the function of A and B.
I beg your pardon, no calculation?
For van der Waals equation.
Oh, alright. Noted.
Okay. Right, so let's just try a few questions. Two of these questions is some extra one. Kalau awak print nota sebelum madam update, kemungkinan awak tak nampak dua soalan ini. So boleh screenshot ataupun boleh salin kemudian ya. Okay, just to show you how are we going to use this van der Waals equation to answer the questions. Okay, so the example question number 1 over here, table shows value of constant A and B in van der Waals equation for gas W, X, Y, and Z. So determine the gas that deviate the least. Okay, deviate least from the ideal gas behavior. Maksudnya dia nak real gas ke dia nak ideal gas?
Real.
Deviate from, right? So deviate least from ideal. So dia nak yang lagi ideal ke nak lagi real? Deviate least from the ideal.
Idea.
Dia nak cenderung kepada ideal ya. This is the keywords. Deviate, yes. Kalau awak nampak deviate, you have to see the full sentence. Deviate, yes, we proceed towards the real gas. But here over the questions, it says deviate least. That means we want a more ideal gas. We want a more ideal gas. Over here, deviate least. Yang paling ideal. Okay. So can you tell me, we prefer a lower value of A and B or a higher value of A and B?
Lower.
Lower. Agree. More idea. Kita nak lagi tinggi value ataupun lagi rendah? If you want to refer to the short note also, can you remember about the last one over here? If you want the more idea gas, we always look for a lower value of A and B. Lower A, it means you have a weaker intermolecular forces. Lower B, it means you have a smaller volume of the gas particle. Okay. So deviate least from the ideal gas behavior. Yes, it deviate, but we still want a more ideal gas over here. So which gas give you the lowest value of A and B? So out of W, X, Y, Z, right? Which one give you the lowest set for both?
W.
W.
Gas W over here, right? It's because we have the lowest value of A, 0.024. Dia hanya value sahaja. Lower value A, it means you have the weakest intermolecular forces. Okay, lowest value B also over here, you have the smallest volume of the gas particle. Sebab ingat kalau awak nak lagi ideal gas, sebenarnya dia adalah negligible intermolecular force and also negligible volume of the gas particle. So in this case, we have gas W. Now, because it has the lowest value of A, it has the lowest value of B. Okay. How about for B? It has a higher boiling point. So if you still remember boiling point, what should you relate it to? Boiling point biasanya relate kepada apa?
Pressure.
Intermolecular forces.
Boiling point, you need to look at the strength of your intermolecular forces. Remember what we have did it previously, yeah? Stronger the intermolecular forces, more energy is needed to break the bond, therefore higher the boiling point. Nampak tak kita link kepada chapter yang sebelum ini? Okay, so in this case, intermolecular forces, which constant you want to relate to? Is it A or B? Intermolecular forces, what you want to relate? Is it A or B? Constant A or constant B? A. Okay. So we want a high boiling point, so that we want a stronger intermolecular forces. So should we go for a higher value A or lower value A?
High. High.
High. So which which gas you have a high value of A?
Z. Z.
Over here. Okay, so kita try tuliskan dia punya explanations ya. So gas Z has a higher boiling point. Reason apa yang kita nak tulis? Boiling point because it has
stronger intermolecular forces.
Because you know it's stronger intermolecular forces indicate by a higher it has we can write over here, yeah. It has the highest because among four of the gas it has the highest value of A, which indicates apa? Tadi yang awak cakap kan, indicates the strongest intermolecular forces. Okay. Of course, you can write on your own sentence, but you need to hit the key points. Higher value of A, stronger intermolecular forces. Dan tadi gas W pun awak boleh buat explanation. Gas W deviate least from the ideal gas behavior because it has the lowest value of A, indicate the weakest intermolecular forces. And then lowest value of V indicate the smallest volume of gas particle. Boleh try buat ayat sendiri. Okay, so is there any questions over this part? Tak ada soalan nak tanya? Tak ada? Ada? No, madam, proceed lah. Okay. This one, I let you tell me how to do. Describe which gas behave less ideally under the same condition of temperature and density. And we interpret first the questions. Behave less ideally. Maksudnya dia nak condition, dia nak untuk real gas ke ideal gas?
Real.
Behave less ideally indicate it want a real gas or a non-ideal gas. So tell me what about its intermolecular forces and the volume of the gas. Is it significant or negligible?
Significant.
We want a significant intermolecular forces as well as significant volume of the gas particle. Sebab kita nak behave less ideal, kita nak real gas. Okay, so if you look at two of these gases given, we have sulfur dioxide, we have carbon dioxide. Siapa punya intermolecular forces is more significant? Try to guess. Which one having a more significant intermolecular forces? Ada kaitan dengan apa? Macam mana kita nak start? This is one of the past year questions. How are we going to start? How are we going to see whether the structures having stronger intermolecular forces or weaker intermolecular forces?
Electronegativity ke?
Electronegativity, is there any suggestions? Not quite to electronegativity.
Polarity.
Polarity, macam mana nak tengok polarity? How are we going to look at this? Nampak formula boleh dapat teka tak?
Size.
Size? Okay, come on, keep on trying. What else we can see between SO2, CO2? We have electronegativity, we have polarity, we have size. What else? Boleh bagi clue
Dominant IMF, the molecular forces.
How are we going to look at this? How are we going to select which is the
Structure.
dominant force? Very good. We need to look at the Lewis structure with the shape, your molecular geometry. So if you forgot, madam will try to remind you. Sulfur dioxide, we have, let me look at what is the time now. Madam takut overtime. Okay, sulfur, valence electron. Madam revise dengan awak sekali lagi chapter 4 ya. Okay, sulfur, what is your valence electron?
6.
Oxygen, we have
12.
6 also, we got 12. So in total, we have 18 valence electron. Sulfur sitting in the middle, we have oxygen on the sideway. Masih ingat lagi ya? Okay, so completing the surrounding atom with the octet electron. And then now we have got 16 electron, extra 2 electron putting in the middle. Is this my Lewis structure? Is this Lewis structure's final?
No.
Not yet, right? So we need to make the sulfur in the middle, the central atom, octet. So we borrow one of the lone pair from the surrounding atom, we're making a double bond. So now if you calculate the total valence electron, just nice, 18. Okay, so if we want to put it into the shape, because now we have two bonding pair, yang ini tak payah tulis, cuma kena tahulah macam mana kita nak tentukan molecular shape dia. So we have 3 electron group with 2 bonding pair, 1 lone pair. Therefore, the molecular shape of our SO2 is looking like this. Okay, it is a trigonal. Masih ingat lagi nama dia, trigonal? Shape lah, trigonal. Dia punya
V-shape.
dia punya electron group arrangement is trigonoplanar, but how about the molecular shape?
V-shape.
V-shape. Okay, kita tak tengok dekat lone pair. We just look at the bonding pair only. It's a V-shape over here. Okay, so tell me about its polarity.
Polar.
It's a polar, right? Because if we draw the polar arrow, it's towards the more electronegative oxygen. Therefore, your resultant dipole moment is not equals to 0. Therefore, SO2 is a polar molecule. So if you look at this type of question, it's linked back to your previous topic that you have learned. Okay, so if SO2 is a polar molecule, what type of forces it has got as a dominant force?
Dipole forces.
Dipole forces. Okay, try to figure out what is the forces you have got in carbon dioxide.
London forces.
Kita try juga lah. Yang ini kita nak practice balik awak punya chapter 4. So let's just CO2. Carbon, what is the valence electron?
4.
4. And then oxygen, still the same. We have 12. In this case, we have 16 valence electron. Okay, so in terms of the structures, carbon in the middle because carbon is less electronegativity. And then surrounding, we have another 2 oxygen. So completing your octet electron for the surrounding, now you have got 16. But carbon is not happy because it is not octet, so we have to borrow. As you know lah, we want to find the most stable Lewis structure. So this will be the structures of your carbon dioxide. If you still remember, to find the most stable structure, we look at the formal charge. But SO2, I treat sulfur as the octet one. Okay, keep sulfur as octet. What is that? The octet rule. Kita tak expandkan sulfur dulu lah ya. Okay, so if you look at carbon dioxide structure, still we have the polar arrow, but both the polar arrow are the same. Therefore, you have mu is equals to 0 because both the dipole moment cancel out each other. Okay, therefore we can say that carbon dioxide is a non-polar molecule. Okay, so non-polar molecule, we got only one type of forces, and what is it?
London forces.
London forces. Sampai sini boleh ikut tak?
Boleh.
Clear ya? Okay. So macam kita sudah out of topic kan? Tak apa, kita tengok balik soalan. Describe which gas behave less ideally under the same conditions of the temperature and density. So we want to find a more real gas with a significant intermolecular forces. So now after we have interpret its polarity, we interpret the type of intermolecular forces. So which gases behave less ideally? Is it SO2 or CO2?
SO2.
SO2 because it has a stronger intermolecular forces. Stronger in this time we say it is significant. Okay, so we write our sentence over here, yeah? Okay, so sulfur dioxide behave less ideally, and you need to give a little bit of reason, explain a little bit more. Because it's dipole forces. You can copy down after you have done the structures on the top over there. Okay, because it's London forces, dipole forces between particles are stronger compare to mention also what is the forces in CO2. Okay, compared to the London forces in carbon dioxide. So even though the questions look a little bit more challenged, it's actually to test whether you can link the previous knowledge that you have learned before with the topic that you have learning now. Dia campur lah antara dua topik dekat sini. But it's actually all linked together. Okay, we have already done until here. Okay, so dekat sini sampai sini ada soalan tak?
No, madam. I don't think so as for now.
Okay, yep. Alright, so remind me again, what should you do in Google Classroom? Apa kerja yang kita ada dalam Google Classroom?
First and foremost, the so-called report for the simulation by the University of Texas, isn't it?
Okay, that one's experiment 4 at the end of this week lah. And this one, that one on your own time. Today?
Oh, never mind. So
Tak, untuk hari ni punya sesi saja. Apa yang kena buat? Dekat sini. Question 2, 3, 4 into GC. Okay, so madam want to remind you about the practical tests. I think we will going to postpone because you're going to come back this Wednesday and Thursday. Okay. One more thing.
Madam, how about the for our lesson for Thursday, the next week?
This week or next week?
On the 28th.
Why 28?
Because that's the second batch of students coming back to college. For those who can't go to college on the 20th and the 21st.
Okay, never mind. That one, madam will update you a little bit later lah. After I've got your itu nanti madam akan bagi tahu. Okay, let me stop the recording first. Kejap ya.